Alright, the purpose of this video is to help you guys out a little bit with question 1 in your homework. That question is partially based off of LU factorization, which we've already talked about. And then the second part to that question is asking you to do what's called a Cholesky decomposition, which is briefly discussed in section 724, but they don't talk about how to do it. So I wanted to show you this example to give you an idea of how to do that in your homework question. Now, if you wanted to practice LU factorization, what we've already learned, I'll go ahead and tell you that if we wanted to do the LU factorization, what we would get would be 1, 0, 0, negative 1 half, 1, 0, 0, negative 2/3, 1. That would be our lower diagonal matrix, or we could call it the unit lower diagonal matrix because it's all ones along the diagonal. And then matrix U would be 2, negative 1, 0, 0, 3/2, negative 1, 0, 0, 4/3. So go back to our lesson on LU factorization and try this on your own. See if you can use that process that you read about in the book and that I showed you in the video, and come up with these two matrices for L and U. If you have any trouble with that, let me know and I can help you out with the process of getting this decomposition. But this is part of what you'll have to do for your question 1 in your homework, is an LU factorization. All right, so if you don't understand how to do this, you'll need to make sure you ask me about it so I can help you with it. What we want to focus on in this video, though, is this Cholesky decomposition. It's a different way of decomposing this matrix A into the product of a lower triangular and an upper triangular matrix. One of the reasons why we do this, well, first of all, if you think back to when we were talking about the LU factorization, one of the reasons we did that is because once you have those matrices factored, then it takes a little bit of computing power to factor a matrix, but then once it's factored, you can easily solve several systems of equations that have that same coefficient matrix A. Because now when you're solving a system of equations based on a triangular matrix, your number of operations is on the order of n squared as opposed to n cubed when you're doing regular Gaussian elimination on a full matrix that's not triangular. So the whole point of these factorizations is to find faster ways to do Gaussian elimination. The reason we care about this type of factorization, L times L transpose, they talk about it in section 724 in your book. I'm not having you guys read that section, but basically the idea is that there's certain types of matrices where you can do Gaussian elimination without worrying about the pivoting steps. So if we can cut the pivoting out of our algorithms, then we can cut down on how much work the computer has to do. So these are some special cases where pivoting isn't necessary, and in this particular case, if the matrix A is symmetric, meaning that the transpose of the matrix is the same thing as the matrix itself, which we have that here. This is a symmetric matrix. These entries match each other. All right, so it's a symmetric matrix, and it's a positive definite matrix, meaning that the eigenvalues are positive. We're not going to go through a whole eigenvalue computation here to figure out what they are. They actually tell you in the book on page 144 what the eigenvalues are. But the eigenvalues are positive, and the matrix is symmetric. So when we have this type of matrix, we're guaranteed to be able to do this Cholesky decomposition, this L times L transpose. And we have the other benefit of being able to do our Gaussian elimination without having to worry about pivoting. So let me show you how to do this Cholesky decomposition in this video, because you'll need to do that for the second half of question 1 in your homework, but they didn't give you any examples of how to do it in the book. The basic idea is I want L times L transpose to equal A. So let's just make up some matrix to represent matrix L. I could use a whole bunch of subscripts. I could call this A11, 0, 0, A21, and so on. I'm going to skip the subscripts here. And since this is a pretty small matrix, I'm just going to call these like ABC entries instead of using all the subscripts. So I'll call this A, B, and C, and then D, E, and F. All right, so here is our lower triangular matrix L. When we factor it, the other matrix should be just the transpose of this. So in other words, instead of A going down that ABD going down that first column, we would have ABD going across the first row. And then if we fill out the rest of this, we have 0 CE, 0 0 F is a transpose of this matrix L. And something you need to make sure you understand here is this matrix L, when we're doing this Cholesky decomposition, is different from the matrix L from our LU factorization. So if it was that easy, then we'd already be done. But it's not going to be the case here. So let's get rid of this LU factorization. This isn't what we're using. We're doing a different factorization with L being something different now. Okay, so we have this L times L transpose, and we want this to equal matrix A. And I'll mention while I write this that the matrix that you're using in your homework question is also a symmetric matrix, and it is a positive definite matrix. All right, so it is a matrix where you're guaranteed to have this Cholesky decomposition work out. If the matrix isn't symmetric and positive definite, then you may not be able to factor it in this way. All right, so once we have this L times L transpose, really our goal is to find out what these entries are, A, B, C, D, E, and F. Maybe you can already kind of see how we're going to do this. Let's just think about what we would have to do to get these to multiply together to give me A. Well, to get this entry 2 in the first row, first column, I would be doing this first row with this first column of L and L transpose. In our matrix multiplication, we would be doing A squared plus 0 plus 0. Those should give me that first entry in matrix A. This should give me 2. All right, so right off the bat, we already know that A must be square root of 2. All right, so let's go ahead and fill that in. A, now we know it, A is square root 2. Okay, And you can kind of already see how this is going to go. Just kind of keep working on finding the entries in matrix A and use a little bit of algebra to figure out what the missing pieces are to our L and L transpose matrix. So I'll go ahead and do another one. If I wanted to find this entry -1 in the first row, second column, then I would be doing this first row, second column with L and L transpose using your usual matrix multiplication rules. That would be √2 times B plus 0 times C plus 0 times 0. And that would give me that -1 entry. So then √2 times B is -1. So then B is -1/√2. Okay, so now we know what B is. It's -1/√2. If you like to rationalize your denominators, you can write that as -√2/2, but I don't really care about rationalizing denominators. I'm just going to write it as -1/√2. Okay, and this is basically all we're doing. All right, maybe I'll do one more just for the sake of making sure you guys kind of see what's happening, but I'll let you guys figure out the other half on your own. What happens if we try to find this entry here, this 0? That would be, that's the entry in the first row, third column. So I'll be using the first row of L with the third column of L transpose. Do we get any information from that? And again, using our basic matrix multiplication process, this would tell me that √2 times D plus 0 plus 0 equals this entry that we're looking for, which is 0. All right, so now we know what D is. D is 0 divided by √2, which is 0. All right, so now we can fill that in. D is 0. All right, so just kind of keep finishing out this process. I'll go ahead and tell you what I got for C, E, and F, and you can do this on your own and check your work and see if you're doing it right. For C, I got the square root of 3/2. For E, I got -2 over, or negative square root 2/3. And for F, I got the square root of 4/3. And of course, you could write that a few different ways. You could write that as 2 over the square root of 3, or 2√3/3, whatever. I don't care. Again, I don't care about rationalizing denominators here. I just care about getting the correct matrix. So you got your matrix L using this basic algebra process. You get matrix L transpose for free because it's just the transpose of L. And when you're done, again, you can double check this pretty easily. Multiply these two matrices together, and you should get back matrix A. All right, so this is just a different way of factoring a matrix into a product of a lower triangular and upper triangular matrix. And we can do this whenever we have a symmetric, positive, definite matrix. And again, if we have this type of matrix, we can avoid pivoting and cut down on some of our computation time. Another type of matrix that they talk about in section 724 where pivoting can be avoided is a banded matrix. I'm not going to get into that here because you're not going to need it for your homework. But the main idea is, what people do in these applications is when they're dealing with giant matrices, Whatever your definition of giant is. Some people say giant is 1,000 by 1,000. Some people, they say a giant matrix, they mean 1,000,000 by 1,000,000. Whatever your definition of a giant matrix is, and whatever your applications are that you're working on, there's certain types of matrices that tend to show up frequently in applications. Symmetric positive definite matrices show up fairly frequently in applications, and banded matrices show up fairly frequently in applications. And if you're dealing with a specific application where one of those types of matrices show up, then it'll be nice knowing that you can skip pivoting, because whenever you're dealing with huge matrices, you're looking for any way you can to cut down on computation time. Little things can add up pretty quickly, where if you use one algorithm to do your Gaussian elimination or to solve your system, it could take a computer days or weeks or months. But then if you find some little shortcut you can take, then it can cut down on your computation time to minutes or seconds. So this is a big research area in mathematics and applied mathematics. People are constantly looking for ways to cut down on computation time, and this is one example of a type of matrix where you can cut the pivoting out, which means you can cut down on that time. All right, so hopefully that helps you with question 1 on your homework. You should be all set for that question now. If you need more help, let me know. And in the next videos, we're not going to be doing every single subsection in Chapter 7. I'm going to be focusing on specifically the sections that will directly apply to your homework questions. All right, so we'll look at some of those things in the next lessons.